Right. In the meanwhile, last night, for those who did not have the chance to see, Fenerbahçe won and is now in the finals of European Cup. On basketball, of course, I'm speaking about. So it was a late night for me, but the presentation is ready anyway. Right. The topic seems very specific issue, so I will start with a little introduction of how this motor works. Actually, the switch reluctance motor was a very exciting option some 40 years ago. But with the dawn of the permanent magnet motors, this option became sort of shadowed by the glamorous performance of the permanent magnet motors, because they were silent, their torque density was very high, and seemingly you could do everything with that. The switch reluctance motor comes next to it. In other words, if you list the motors regarding their torque per unit volume issue, what comes out is that the permanent magnet motor comes at the top, and then comes the switch reluctance motor. The switch reluctance motor is an exciting motor because the rotor side has virtually just nothing which makes it structural problems significant. It is just some pieces of iron sticking out of a cylinder, and therefore it's a very rugged type of motor. It cannot replace the induction motor, of course, in standard industrial applications, but in all variable speed applications, it is a, it has a performance which promises a lot. There appears to be a significant problem from the point of view of perhaps mechanical engineers more than us. The issue is this. As I will show you in a moment, the operation of the motor is not as continuous as the induction motor. In other words, you don't have a smoothly rotating magnetic field where the rotor smoothly follows the rotating field. Therefore, the torque is nice and constant, and there is hardly any ripple on it. By its principle of operation, the switch reluctance motor produces torque, and then there is sort of a gap, and then the next phase is switched on, it goes there. Therefore, there are peaks and dips in its torque curve. Now, if you have a big inertia in the system, this hardly makes any effect on the speed of the shaft. So it looks fine. However, the torque fluctuation is there. So what is the significance of this torque fluctuation? Now, this is an issue which is difficult to answer for us, but there appears to be two answers to this at this moment, as far as I know. One is that you have noise. The noise is not only due to the torque variation, which may cause some cluttery noise from gears, boxes, or from your coupling. That is one issue. The other is the fatigue issue, which as electrical engineers we are not so much aware of. Now, of course, with this high torque density, this kind of motor appears to be very suitable for electric car applications. So in fact, the switch reluctance motor returned with the help of Chinese because of unreliable permanent magnet prices. I think Burak showed some figures. The prices in your figure were like $80 per kilogram.
Yes.
But at one stage it was about 200 US dollars per kilogram. So now think of the 20 million cars produced every year. If each car uses 10 kilograms of permanent magnet, that makes 20 million kilograms of permanent magnets. At the moment, most motor manufacturers use neodymium boron iron magnets, and neodymium boron is a very difficult material to extract. I have seen some pictures of how it is produced in China. The conditions are worse than a melting pot where you melt iron with labor, you know. But there are deposits in US, in Canada and Australia, which they try to exploit and develop the process so that it can be cheaply produced. Even then, the 20 million cars using 10 kilograms of permanent magnet each makes the problem a serious one. Besides that, of course, the wind energy applications are spreading, and these are gigantic machines which use a lot of permanent magnets. Reza is not here, I think. We developed a permanent magnet wind machine for direct drive, and the amount of permanent magnet is 30 kilograms for 50 kilowatts of output. Because it's a direct drive generator, it is big. The idea there is to eliminate the gearbox, which is a lot of weight, and the generator size is probably is greater than a system whereby the generator is connected to a gearbox and then to the turbine shaft, which is rotating at a low speed. What the advantage do you expect from that? What you get is that the amount of weight you place on top of the tower is reduced, and therefore the whole tower structure becomes lighter, and hopefully this will reduce the overall cost of the system. Furthermore, although the gearbox is a very reliable thing, its efficiency is maybe 98-99%, and it is currently we don't produce such gigantic gearboxes. Now, this study originally started to develop a software which could design the switch reluctance motor. The analysis of the switch reluctance motor is somewhat different than the conventional motors. And it starts or relies on the principles of energy conversion. What I mean will become clear as we go forward. I'm just showing this picture for those who are not familiar with the structure of a switch reluctance motor. What we have here is, for example, this one has 4 pairs of opposing stator teeth, so you can conclude that this is a 4-phase switch reluctance motor. The operation will be clear in a moment. So what you do is actually you excite this pair of saliencies. The rotor saliency aligns itself with the excited phase. When you switch to this one, for example, in this particular one, the alignment will be in the counterclockwise direction, although the magnetic field is rotating in the clockwise direction. This is a peculiarity because of the less or smaller number of teeth or saliency on the rotor side. The general rule is that if you have smaller number of saliencies on the rotor, the rotation of the shaft is in the opposite direction to that of the rotating field. Actually this type of thing can be used as a generator as well. So this could find application also for wind applications. The advantages I briefly mentioned. It is a simple structure, easy to manufacture. The rotor losses are small. Why? Because this is a synchronous motor and therefore the rotor has no loss. So it looks ideal for for electric car applications. And actually I have read in some places that this will be the next option to consider for the electric car. The reason perhaps why people did not start with this is this is a rather difficult to design machine, so not many people know how to handle this issue even in industry. And also the famous vibration or torque ripple issue. We will come to that later. The drive itself is simple. Actually, you can drive this kind of motor also with a sinusoidal excitation. Who was the friend from Negev in Israel? There was a professor in southern Israel. What's his name? Rabinovich. Rabinovich has some papers on that. Another issue with the switch reluctance motor is that you need a position sensor, but the position sensor doesn't have to be a high resolution one. You can simply sense the place of the stator poles, and that's probably enough. In other words, 4 pulses per revolution may be enough. Okay, now these two pictures look at carefully. In this picture you see the bunun şeyi neredeydi ya? Şurası mı? Ha. You see that the stator teeth is not aligned with the rotor teeth here. Look at here. So this is how the motor is rotating. Now, to give you an idea of the type of motor we work on, this is the application we considered. Now, the brown part that you see in this picture is the core. The sort of greenish part, it is actually blue, is the part where the end of the winding, end winding sticks out. Now, as you see, the rotor is very tiny here, indicating that this is a high-speed motor. This motor is designed to operate at 16,000 RPM. In fact, the application is a very familiar one. This is designed for a washing machine application. The washing machine is a very demanding application. The washing cycle requires about 400 RPM. I'm speaking about the motor side. There is usually 1 to 10 reduction. Therefore, the actual tank in which the clothes are kept rotates at about 40 RPM. But as you know, it spins in one direction and then in the other direction. And for drying purposes, the speed goes up to 1600 RPM, and the motor has to go up to 16,000 RPM. Actually, it turns out that the active material used in the machine becomes really small, and it can be half the amount of material used in a conventional induction machine currently used in washing machine applications. But the converter is more complicated. Just to understand the equations that we shall be giving in a moment, let's have a look at this. For example, in this one, you turn on these two transistors, you let the current go, and the current rises like this. When it hits a top value, you then switch off, for example, this transistor. The current circulates in this one, like this, and the current starts decaying as shown here, and then once again you go back to this situation where the current rises again as here, and then when you switch off, the current decays. Now the issue is that if current decay is not fast enough, there might be negative torque produced by the off-going phase. So sometimes you apply a negative voltage across the off phase so that the current decays fast. Okay, now what do we want to do? If you want to design a motor, you have to be able to calculate its performance. Now, for an induction motor, that's somewhat easy. In other words, most induction motors are designed for operating at constant speed. Therefore, you have one set of equations which handles the problem. But when you speak of designing a variable speed machine, the situation is different. Although none of the induction motors available in the market are designed for this purpose. Of course, I'm generalizing. Maybe for specific applications they do. But if you are designing a switch reluctance motor, which is going to operate from 400 RPM to 16,000 RPM, you cannot just say, okay, I designed this for 16,000 RPM, I don't care what it does at 400 RPM. No, it's not like that. You have to make sure that it performs as required. Also, the speed range is very wide. In some occurrences, you might have to provide a certain amount of torque at a certain speed. So the issue is totally different. What do you need in that case? What you need is that you need a method which allows you to calculate how much torque will be produced at each speed, so that you can assess whether a design that you made is acceptable or not. Of course, you need the phase current, you need the losses, core losses, and the static performance may be important, so you need to predict that. Now, existing software in the market access this static torque curve via rate of change of co-energy of the system, which relies on a differential equation, which becomes a difference equation in real application. Difference equations are risky because any error that you have in the calculation of the quantity at the top is magnified by the small time step you have. So the prediction of the static torque curve is not easy. Of course, I'm referring to analytical calculations here. Most people now just use brute force, so to speak. They go to a finite element program, solve the magnetic field, and they say, ah, great, I've got the torque curve and it is exact, it's nice. Yes, that's possible. But of course, if you are optimizing, the options are almost infinite. And if you are going to do that, by finite element solutions. It would take a tremendous amount of time unless you have Brack's supercomputer where you can run 1,000 tasks at one go. But of course we are speaking about a standard industrial guy. Now these are the things that we want to know on the paper, and these should be accurate enough so that we can actually say, okay, our design is good. Nowadays, a design exercise should not involve more than 1 or 2 prototypes, and the design should end there, because otherwise the cost is very high. Now the control parameters are, besides the current level which you want to apply, is the instant you turn on a phase, how long to keep the phase on, and the turn off angle. Now why is that important? As you noticed in the picture, you turn on a phase and the rotor aligns with it. If the motion is slow, it's not significant how you turn on or when you turn on the phase. But when the speed increases to 16,000 RPM, the time constant of the phase where the current, which the current rises with, becomes comparable to the available time for the motion of the rotor. And in that case, to get some torque, you should turn on the phase before the actual place where the positive torque is being produced. So you turn on the phase early, where the phase which is going to turn on produces negative torque, but the current is very small, therefore the negative torque is small. But when the position in which the positive torque is being produced comes, the current rises to a reasonable value so that you start getting some torque. This is the same principle that we apply in our combustion engines, where we advance the spark so that by the time the spark develops into a combustion, the cylinder is in the right position and you get some torque from your combustion engine. Now this is the basic principle which in fact can be applied to any motor. Any motor can be represented with a resistance, a leakage inductance, and an induced EMF. Now, this inductance doesn't appear in this equation because it is enclosed in this flux linkage term here. So, forget about this resistance for a moment. When you apply a voltage, what you see is that the flux linkage would linearly rise to a certain value. Now that certain value is your design value. In other words, it's the value at which your core starts saturating. So you say, okay, stop. You have reached 2 Tesla in certain places. Now let us reduce the flux linkage, and you apply negative voltage. Then what you get is a triangular flux linkage shape, which rises when you apply positive voltage and which decays when you apply negative voltage. So there is nothing new in this model. This dates back to 1974, when I was actually with this group, and but it's a very effective formulation. And there is one more equation to consider. It is the mechanical equation. You produce some torque, the load torque is there, the difference goes to accelerate your inertia. So if you are going to consider the motion, which you should do for torque speed curve, this is the second equation. So what you should do is to solve these equations simultaneously to obtain the torque speed curve of this motor. What you need is quite obvious. You need this. If you know the variation of flux linkage against time, or replace time with theta here and place speed here, then what appears to be needed is the variation of flux linkage with current and position of the rotor. If you have that, then you can solve this equation set. Now, you see some curves here. The vertical axis is the flux linkage, the horizontal axis is the current, and each of these curves correspond to one particular position of the rotor. Now, how do you measure this? This is somewhat, it looks complicated, but it isn't. This is like measurement of inductance. So these curves can be measured for sure. But of course, when you are designing, you don't have the motor, you cannot make measurements, you should be able to calculate them. And one important issue here is that the variation of the flux linkage is linear at the bottom, and it becomes like the BH curve of a core material when you go to this place. Obviously, this position corresponds to the unaligned position of the teeth, where the reluctance is high and the current level you apply is not enough to saturate the core. But when the alignment occurs, the reluctance becomes small and the same current saturates the core, and therefore the curve behaves like the BH curve of the core material. So you are actually inching away from one position to the next and progressing to the final position you want to go. At what speed do you go? Now, obviously, you are not crazy, and you assume that I will consider steady state condition where the rotor speed is constant. So what you have to do is to solve these equation sets several times for different speeds, say 4 or 5 speeds of interest, where you could calculate the torque. So the speed is considered constant in this analysis here. Now, the problem that this paper deals with comes from this fact. Now, these flux linkage curves are obtained, say, from 2D solutions, because that is less time consuming. And there are professional software in the market which try to approximate the magnetic circuit in 2D so that these curves can be calculated. But if the stack length is not long, the calculations are erroneous and the prediction accuracy is poor. This shows how the time step is taken. You go from current 1 to current 2, and the motion actually takes place, the flux linkage variation actually takes place from this point to this point. This, anybody who has taken energy conversion would be familiar with this. I'm not going to spend a lot of time on this. I have given you the basic idea. So what you need is flux linkage position and current position curves. Now, this is what is available. In other words, existing analysis methods rely on this. But what we have done is to produce a set of data which is dimensionless. Now, what do we mean by dimensionless? In the dimensionless world, everything is one or less. In other words, they are normalized with respect to the pitch of the poles. So when you speak of tooth width, you say 0.4, meaning that it is 40% of the pitch. When you speak air gap and the pitch of the pole are the two normalizing factors. From this data, you can predict the flux linkage curve of any size of switch reluctance motor. Furthermore, we have the static torque curves data, which also gives you the static torque curve of any type of combination for switch reluctance design. This is showing the finite element solution. The blue curves are the finite element solutions. The black, rather the reddish ones are the predictions from our curve. So this is showing the static shape of the static torque curve for those who do not know. what you have here is the excitation torque, and on this axis you have relative position of the rotor with respect to the excited phase. Now this is the phase current, typical phase current. If you know the phase current, it is possible to calculate its RMS value. You can calculate the copper loss quite easily. You need to calculate the core loss, of course. This is a more complicated issue. I'm not going to spend time with this. So at the end, as I told you, this phase is turned on, the flux linkage is rising, it is decaying, it's turned off, and the flux linkage trace is like this. And anybody will remember that the torque, average torque, if you are interested in average torque, the average torque is the division of this area inside this loop to the motion that took place. Right, so what we learned from here is that we have a set of data from which the flux linkage curve can be predicted. But the data is produced from 2D field solutions, and the third dimension is not included. Now, maybe I skip a little bit here to the clever things we have done. Okay, so this is the motor on which we exercise our method. Now, what we mean by the end leakage is the leakage in the third dimension. In other words, this is the core. Some flux will be circling out and then coming in on either side. Now, in a 2D solution, of course, you do not consider this. You just consider this plane where you have these sticking bits and you assume that it extends to infinity. So what is needed is to be able to predict these arrows which go out of the motor and then come back in from the ends. And its effect could be quite significant, as we shall see in a moment. Now, this problem is quite complicated, obviously. Look, here the rotor is aligned with the excited phase, and the flux paths are more suitable for the flux to go out and then come in. But when you come to this, as you see, the rotor is unaligned here, so obviously less flux will be leaking out to go to the rotor side. So in other words, we are facing an effect which is also position dependent. And now, well, you may say, this is not important, let me just calculate 2D, but when you do that, you will see that the error can be quite large. Now, how do you take this into account? This problem appears to be very difficult because the truth are the poles in which the flux flows is maybe have a uniform flux density at the top, but when it comes to the bottom, where the air gap is, the flux accumulates in certain regions, going out of the pole like this, and therefore the corners here saturate. Now, this is the side view. You can see the core here and flux leaking out. This is the end winding. Look, this leakage is not what you have on the end winding. The usual leakage is the flux circulating around the conductors, which is at the end of the core. This is the flux leaking out because the core is saturated, and therefore the flux is leaking out. Let the core not saturate. Okay, let's do so. But the problem is the motor becomes very large as soon as you do that. And remember, we are competing with the permanent magnet machine, which is already very small. So, how do you solve this problem without really using finite elements? Now, fortunately, there is somebody called G.W. Carter who lived at the beginning of the last century in 1900s, and I had the opportunity to meet his son. And obviously he was a very clever man. What he did was very intelligent. What he did is, they were facing this problem where they were designing generators and they needed cooling ducts. And here, this is the air gap. This is the cooling duct for them. And they need to calculate the inductance to make the design. So how do you do this? What he did was to map this structure, which has lots of air space here, to a problem whereby two parallel surfaces faced each other. In other words, he mapped, for example, this one here to this one. What is changed here? This mapping allows for the flux going through here by extending the core a little bit or by changing the air gap, but at the end you end up with two flat surfaces which have the same reluctance as this structure here. So this is equivalent to this. That's very clever. So now, although we don't have such a situation, you can imagine that there is a mirror stack. This is your actual motor. This doesn't exist. But suppose it exists. Then you face the same type of geometry. Okay, you say the distance here is this much. So can I replace this cross-like structure with two surfaces without any leakage out, but which has the same reluctance as the actual structure? Now the problem is, how do you decide what distance between the two mirror images is rather? So do you get the problem? This is an artificially created problem. We don't know what this distance between the two mirror image structures should be, so that we get the correct answer for the flux leaking out. Now Carter's approach is that you will have a flat surface with this artificial length LCF. This is the original length. This is the distance between the cores. This is the Carter's coefficient, which he calculates from this equation here. So he's replacing this slotted structure with two flat surfaces as in here. Okay. Now there is another issue. As I told you, the rotor moves and the end leakage is a function of that too. That makes the problem further complicated. Our model relies on the two surfaces being exactly against each other. But at times our rotor position with respect to the stator is like this. So what we should do is to find an equivalent structure where the two facing surfaces give the same reluctance as this one. So we have a two-stage problem. First of all, for any position, convert this to this, and then use the previous approach to calculate this equivalent magnetic geometry, which gives you the same reluctance or permeance as the original structure. So this is what we do. I think you got the idea, but perhaps you did not understand it completely. So we have a two-stage issue. One, account for the rotor position. Second, calculate what amount of end leakage there is. So the calculation is pretty accurate in that respect. Okay. Our model actually takes into account what we call the taper. Here you see two parallel sided tooth here, but in practice you sort of introduce a taper where the area through which the flux goes gets wider, because you don't want any MMF lost on your way. Okay, so we used our data to convert this actual situation to this one. We go to the data and find the equivalent structure which has the same permeance as the original, which is original is here, and take it. And then we use our mirror image model to calculate how much end leakage there is, and that's it. So this is the typical variation of permeance against tooth flux density. I place this to show you how the tooth saturates and the significance decrease in the value of permeance. If you don't calculate this properly, you are in trouble. Okay, now how do you decide what the value of n should be? What we did was to do a series of field solutions by changing the distance between two mirror image structures so that the distance became insignificant. If we place them too close, the mirror image, which doesn't really exist, starts affecting our field distribution, and therefore the result is wrong. And if we place them too far apart, we are introducing unnecessary problems for us, and therefore via that we found out that if you, this is significant and it's worth remembering, 40G appears to be this magic number. Any magnetic structure which is away from each other by 40G appears to have no effect on the close vicinity of the wider magnetic device. In other words, the field distribution is not affected by the presence of the other piece if it is far away as much as 40G. What's G? G is the air gap. So if the main flux is flowing through a gap of G, any other magnetic structure placed away from that by 40G is not affecting the mainstream flux so much. So it is for all practical purposes, it is acceptable. Now, here, this top structure, top graph is without end leakage, but this one is with end leakage. There is no difference. So why did we do this? But this is in the alignment position where the flux is a lot, and therefore the end leakage effect is small. But when you get away from that position, you see the end leakage becomes significant. Here, the dots are measured. The solid line is calculated. But when we make the correction for the end leakage, the two curves stick to each other as shown here. So this is a good indication that our predictions will be better. This is the torque speed curve predicted for the test machine with no leakage, end leakage effect. Here with end leakage effect. So the improvement in prediction accuracy is significant. There are some more examples here. This is another example. Our colleague Rasul did this study. This is a electric car motor developed by Akira Chiba from Japan, and this is a very recent paper. Now, obviously, he did not have the tools to study this problem in detail, so what he did was a sort of brute force approach, where he, of course, he's a very experienced person. He guessed what he should do and made certain assumptions, and he designed a motor like this, which has a, listen to this carefully, the diameter, outer diameter is 20 centimeters. The core length is 20 centimeters. This is 50 kilowatts. Now, a 50 kilowatt machine of the same power in an industrial size would be about this big. Of course, it's water cooled, right? It's water cooled, and this is also significant. The current densities reach 20 amps per millimeter square here. Normally, even 35, yeah, 23 maximum, 33, yeah. So the peak current density is 33 amps per millimeter square. The average is about 20. In an industrial machine, this number would be about 6 or 7. Of course, with the efficiency concerns, these numbers are being revised at the moment. So, what we did, this is just to illustrate that our analytical approach is giving reliable results. We also sought other issues. For example, how many teeth should you choose on the stator and how many on the rotor to optimize this motor? In fact, Russell found out that he could obtain more output, 20% more output. How much? Output more? Yes. How much more torque would he obtain if he optimized it properly? 15%. 15%, yeah. Okay. So this, for example, shows our analytical predictions, and the dots are again the finite element solutions. Here, as you see, our predictions are quite accurate. And from here, we calculated at a certain speed here, for example, 1200 RPM. These analytical calculations, 4.6, FEM 364, measured 366. Ooh! What happened to our good method? 10% error. In fact, the reason why we had this error is the BH curve. This is the material Akira Chiba uses. The blue curve is what we use. Now, it turns out that this is significant. When we change the BH material, the material that is used in the application, as you see, the finite element solution gives almost the same result as our data. In other words, the approach is correct, but what it tells us is that the material property should be taken into account if you want accurate predictions. Now, the torque appears to be very close to the measurements, but don't think that it is a nice smooth torque. Here is what you get. Look, here is nearly 30% torque ripple on the shaft. Ooh. So obviously one should look into ways of minimizing this torque ripple, and I will cut it short here. Thank you very much for listening to me, and this is the end of my first presentation. Thank you. 10 dakika ara verelim. Bir çay içebiliriz bulursak. Efendim? Orada yazıyordu C bilmem ne diye bir şey, yani özel bir malzeme ve 0.1 milimetre kalınlığı var. O niye acaba ilk başta normal ses de yeteri kadar çıkmıyor? Çıkmıyor mu? Ha.
Biraz yakın olmak gerekiyor hocam, ben
az geliyor ha? Ha. Sesi açalım. Alo. Ha, sana geliyor sesi, öyle mi sadece? Ha, ben burada mikrofon var diye hiç şey yapmıyorum. Ha, sana geliyor sadece ses. Ha. Tamam, anladım. Obviously this microphone is just for the recording, not for the audience. I ought to speak a little bit louder maybe. Was it understandable, Doron? Huh? Yeah. Do you able to hear what I say? Here. Right. Now this next presentation is about a control moment gyroscope for a low Earth orbit satellite. Now, a little bit of information on this. The low orbit satellites circulate the Earth around an orbit which is completed in 80 to 100 minutes. Therefore, you have a window in which you can observe a certain part of the world from the satellite. So once the satellite is gone over that part of the Earth, you have to wait another 60-80 minutes before the same position is gained again. Therefore, this problem arises when you, for example, the first satellite developed for this purpose was for identifying the crops in Turkey, and therefore you take pictures and then you process the images to find out that next year there will be 20 million tons of wheat and 10 million tons of sugar beet, whatever. So this is the idea. Now what you should do is to take as many pictures as possible when this window is available. Now the satellite is at the top here. Of course, you should target your camera to the location you want to picture. Now the first thing that comes to mind is, okay, just don't bother with the satellite, just play with the camera and focus it to the area you want it. But of course, as soon as you start playing with the camera itself, the satellite structure also moves, and therefore taking a stable picture is not possible that way. What people do to solve this problem is that they move the whole satellite. I speak about photographs, but of course for communication also you need to focus the antenna to the antenna on the Earth so that a health signal is received from the top. Therefore, this alignment of the satellite for the purpose you want is called the agility of the satellite. It should be able to do what you want quite fast. But of course, in space there is nothing to damp your motion, and in fact this issue is becomes quite a complicated task. So what people do is to establish a pyramid with a triangular bottom. So you place 4 force actuators, so to speak, which all generate force in a certain direction so that the resultant torque is in the desired direction and that the satellite body moves in the direction that you want. But of course this gets more complicated because when you start the motion you should be able to stop it also. So you actually have to damp out the motion by creating force inside the satellite once again. So when it is overshooting the location you want to stop it, you ought to have a strategy which would bring it to the exact location you want and then stop motion there. Anyway, that's not our issue. As electrical engineers, we are more concerned with the force actuator itself. What do people use for this purpose? There are several solutions. They use actuators. There are several types of actuators. One is reaction wheel and momentum wheel. These are simpler actuators in which you have a mass rotating at a certain speed. When you want to create a force, you slow down the mass and therefore a force is created. Or you accelerate the mass. These are simpler actuators, but the problem is they tend to saturate. In other words, you are doing a certain maneuver and you are decelerating the wheel. I think Arda told us something about this. You decelerate it to a certain point. Afterwards, there is not enough energy in the wheel. Therefore, you must accelerate it once again to the speed you desire, and then to obtain more force, you decelerate it again. So the issue restricts your strategies for aligning the satellite itself. The control moment gyroscope is not like that. Let's see what a control moment gyroscope looks like. A control moment gyroscope can be simplified like this, where you have the satellite structure here and a wheel is rotating around the shaft, and there's a gimbal which you can turn around. Therefore, the plane in which the wheel is rotating can be changed. Therefore, in the z-axis, which is perpendicular to this plane, this is the plane, and the force is sort of orthogonal to the rotating wheel in the direction shown. Now, obviously, if you are speaking about a satellite application, the weight of the gyro becomes important, especially when you think that you will have 4 of these at least operating simultaneously. The reason why 4 are needed is to provide some redundancy, of course. In this particular application, this is a smaller satellite. The main motor is the motor which drives this wheel. The gimbal motor simply changes the plane of rotation. And of course, you use it only when you need to do some maneuvering. And therefore, the other motor, the gimbal motor, is not often used. It's only a 5 watt motor in this application. The other motor is about 35 watts. This is the prototype designed by the Turkish Aerospace Agency, and the reason why I show you this is that in this geometry, here is the wheel motor. This is a standard commercial off-the-shelf motor. There is a coupling here. The motor has 2 bearings, and you see here a strengthened bearing is used, at the end of which this wheel is rotating at 10,000 RPM and storing energy. As you see, the weight of the wheel is on one end, the weight of the motor is on the other end, but this is a sort of top-heavy construction, and therefore when this gimbal motor here rotates the shaft, it has to counter the torque arm here and the weight here. So the force on the motor shaft is because of this shaft being at a distance from the center of the rotation axis. This is not a good design. Furthermore, because a commercial motor is used, this space here is wasted. And obviously this design would occupy a lot of space in the satellite. It is only a small satellite, therefore the space is very limited too. What is the requirement? The wheel is required to be accelerated to top speed in 35 seconds to 120 milliseconds. This is the inertia, the speed is known. So this defines the amount of torque needed, which is 50 millinewton meters. But once the rotor accelerates, you need a smaller torque, of course, and therefore this is the peak torque in a way. The efficiency of the used motor is 78%. Now this, of course, is very important because here 22% of the energy is wasted, and the first satellite went down because of failure of the battery and the power supplies used for that purpose. Furthermore, the energy is very limited, especially when the satellite goes behind the Earth. There is no radiation, therefore no power is produced. Therefore, the power supply is allowed to fluctuate between 24 volts to 18 volts until the sun is again visible and the battery starts charging. Anyway, that was the specification given for that. Now this shows a test whereby the system is tested. The dots are experimental. This is the quadratic approximation to this acceleration. This is the load that we should accelerate, in other words. But in space, of course, the situation is a bit complicated. There is only the friction torque we should beat. There is no friction, there is no windage, so to speak, and therefore the torque that will be experienced by the motor will be less than this. This torque is required because we have 4 bearings there, and therefore the number of bearings is also an important issue. Less the number of bearings, you can make it a smaller motor. Therefore, you use less energy from available in the batteries. This is important because then if you have enough energy, then you can introduce more tasks for the satellite. So the purpose should be to make a compact structure. One can immediately think of 2 solutions. One is to make a inside-out geometry whereby the stator rotates and the stator can be used as the inertia of the motor. The alternative is to design an axial flux motor. Look at this here. This is the existing structure. This is the wheel. This is the supporting structure. But if you use a double rotor in the axial flux motor, in that case there are 2 pieces out here and the stator is here in the center. It is stationary. This is a toroid. In fact, it looks like this from the top, but it is a toroid in here, and these are the wheels which you can use as inertia. This picture is more enlightening. This is the stator, which is stationary. These are the rotors which rotate, and they have permanent magnets on them, as you see here. So this structure in principle looks very promising. Because of the balanced structure, because of the 2 rotating pieces on either side, this is going to present a balanced load for the gimbal motor as well. Now, when you start thinking about the axial flux motor, several options come out. Let me explain what I mean. You can make the permanent magnets on opposite sides of the same polarity. So we are looking at from the top, and we are looking at a position where 2 permanent magnets on the 2 rotors are facing each other like this. In this case, you can use a winding which on the toroid. The center becomes a toroid, as you see here. The winding is around the cylinder. Or you can have this topology whereby the opposing magnets are NS polarized. In that case, the winding is on the surface of the cylinder here. Not like this, but here, on the surface of the cylinder. This, of course, we evaluated both, and the toroidal structure appears to be the best choice in that respect. Now, the material choice is very important here. In space, of course, there is lots of radiation, and the magnetic properties of the materials deteriorate. Also, corrosion is an important issue, and it appears that the best option would be to use samarium cobalt, which can withstand very high temperatures. Now the problem is, when the satellite is facing the sun, the temperature on that side rises a lot, and the other side is cool, and the permanent magnets may be exposed to high temperatures. And of course, the purpose is to reduce the risks as much as possible. And thermal conductivity of the material is also very important. Now, since there is no air or any conducting medium, the only way of disposing the heat generated inside the motor is via radiation from the motor itself. So the cooling issues are very important. So at the end we decided using this permanent magnet, which seems to satisfy these conditions. Now this is a 6-pole motor. Why 6-pole motor will become clear as we go ahead, and the frequency will be 498 Hertz, which is quite high. This requires a square wave drive for this, and there is nothing much you can do on this issue. These are the core material properties. This is a low loss sheet steel. As I told you, the dispensing of the heat generated is difficult. Therefore, a good quality material is required. Now, if you have ever worked on permanent magnet motors, you would know that square wave excitation promises to provide about 5% more torque, but the torque ripple may be an issue in this matter. Furthermore, since the frequency is high for an inverter, we opted for square wave excitation. We did not, at this stage, give much emphasis to the torque ripple issue. We just wanted to test whether we can actually achieve our purpose. Now, when you look at the inside of this motor, you can see the discs here with the permanent magnets on them. This is the toroid with the winding on it. This is the general structure. Now, if you drive the equation for the torque to be obtained from this motor, now we are trying to design the motor, size the motor, so that this task can be performed. What we shall do is this. We shall design the motor for what number of poles. So, since we don't know the answer to this, we should try different designs with different number of poles. What is our criteria of design? Two things. Make the mass small, make the volume small. They may not be the same thing. The volume is important because the space in the spacecraft is limited. The mass is important because, after all, you are lifting off this satellite, and therefore, if you make it, say, 100 grams less, perhaps you can put another electronic card into your system. Now, here, R is the outer diameter, KR is the ratio of the outer diameter to inner diameter of the toroid that is located in the center. There is some research in the literature which gives the value of KR against efficiency, and for a certain flux density value. This person's study shows that at about 0.35 Tesla, the best values of Kr is in the region of 0.3 to 0.8. So this gives a good clue as to what one should look for. Now, so we are aiming to reduce weight, and the air gap flux density is important issue because we do not want too much loss there. That might cause a problem. And the other issue is actually if you are going to manufacture this, the magnet material, the shape of the magnet must be manufacturable. If you theoretically design the best magnet but it cannot be produced, it is no good. Actually, what happens when you analyze is that the design tends to push the magnets to a very thin layer, which is not manufacturable. So we place the limit on that as well. So what we did is that we plotted the variation of the mass of the motor against flux density, and also the inertia of the motor against flux density. We want big inertia with the smallest volume possible. And the optimal values seem to be around here. The inertia is reasonably high, but as I told you, when you go towards this end, the magnet becomes non-manufacturable, and therefore we decided to choose a flux density in this region. Do you see this graph is showing the air gap magnetic flux density against magnet thickness. After some point, if you further increase the magnet thickness, the flux density in the air gap does not increase much. Obviously, there is not much point in going beyond this. This corresponds to 3 millimeters, but the knee point is the best place to choose, as most designers do when they are designing magnetic circuits, and that comes out to be 0.32 Tesla. Now, the next issue is the current densities. So we know that the only cooling is available via radiation, and for this we refer to the previous solutions whereby the current densities were already tested in space, and therefore for acceleration instance, the electrical loading is chosen about 4,800 RPM. This may be difficult to visualize for some of you. This corresponds to about 7 amps per millimeter square. During the steady state operation, the loading drops to 3 amps per millimeter square. The toroid winding, of course, occupies space in the air gap, and in this case this thickness of the winding is 1.14 millimeters, and of course this is rotating at pretty high speed, and therefore you should leave some spacing between the winding itself and the facing cylinder, which is the inertia, and that is chosen as 0.5 millimeters. No matter how good bearings you use, you must allow some slack for that. And the next issue is, once you have done the design, you should be able to calculate its performance. The magnetic circuit of the axial flux motor is represented as quite simply by a resistance, an inductance, and an induced EMF. And the inductance is the important issue, and we designed several motors with different number of poles and calculated their inductances, and then I will skip this. I will give you something more important. Of course, when the voltage drops to 18 volts in the battery, you must consider the voltage drop on the semiconductors, and this leaves only about 8.5 volts for the motor phases. At any given moment, two of the phases are in series, therefore that makes 16 volts, plus the drop on the semiconductors, the total is 18 volts. The back EMF at 10,000 RPM is the highest value because we have no field weakening here, and that should be at a value so that the desired torque is still produced. If you cannot push enough current, that torque will never come through. So the first thing you should test is whether you are able to push current into this motor even under the worst conditions. This is the plot of current into the motor as the speed rises, and it happens that this motor is capable of pushing about 1.6 amps even at 10,000 RPM. Now I will skip these graphs here. These are the losses. Look, the two-pole motor losses are higher, although the six-pole motor is running at a higher frequency. 468 RPM, 468 Hertz for this, about 140 Hertz for this. So the losses are less for the six-pole motor. This is the efficiency, and the dashed line is the efficiency of the two-pole motor. Blue line, solid line, is the efficiency of the six-pole motor, which appears to be better. But at 10,000 RPM, their efficiency comes quite close to each other. This region, you may say, is not very important because it's only a transient situation, but any energy is valuable in the spacecraft. Now this compares torque per unit mass for the two-pole axial and six-pole axial motors. You can see that the torque density is much higher for the six-pole motor. On the right-hand side here, we see the radial flux option. Again, for the radial flux option, the solution indicates that the six-pole solution would be better, and however, the radial flux motor is not able to produce as much torque as the axial flux motor. In comparison, there is about 25% less torque in the radial flux motor as compared to the axial flux one. This is the mass graph. As you see, the mass of the two-pole machines are larger as compared to six-pole options, and the six-pole option for the axial flux is the one which has smaller mass. This is the torque versus volume graphs. Again, the six-pole option for the axial flux appears to be the best. Now, how do we compare the volume? This is the volume occupied by the existing design. The present design, look, the new design is very compact. These are the portions which we should add to get the amount of inertia we require. They are just mounted on the rotating bits of the motor, metal pieces like this. And the comparison shows us that with this design, the efficiency of the motor improves from 78 to 93%. Volume of the wheel system is nearly 2.5 times smaller. Mass is reduced from 530 grams to 360 grams. And this design appears to be very advantageous. So, this is the message. But we should verify this design, of course. For this purpose, what we did was to model this with finite elements. The issues now are, first of all, is our analytical method giving enough accuracy so that we can rely on the results? Second, what's the torque ripple? Third, what's the temperature of the motor in space? These are the results of the field solutions, and as you see, the ripple torque is very high here. It is 30%. Now this is not acceptable as it is, and therefore it indicates that something should be done to reduce this torque ripple. You see the current here. Now what are these peaks here? These are the instances in which the other phases are excited. So we should do something there to smooth out the rise of current in the other phases, so that the induced effect on the conducting phase is not as serious as it is in this particular one, and therefore we control the torque ripple here. This problem, I believe, can be solved, and here is the comparison of the finite element solution and our analytical solution. The efficiency comes out even greater for the finite element solution, and the phase voltage prediction we made is correct. Electric loading prediction is slightly less than what it is observed to be in the finite element calculation, but in general the matching is quite good, and this approach we developed can be used for the design of the motor required for this application. Okay, I cut it off here. I think that's enough. If you have any questions, I can gladly answer. Yeah.
Thank you very much for the presentation. I have a question about the slide of 28.
Okay.
Sequences of magnets.
Okay.
Actually, I wonder about how you decide the limit 28.
Okay. Now this is somewhat arbitrary. It could be any point from here to here. It would make little difference. The flux density we chose was 0.32. We could choose up to 0.45, but as you see, the curve is tailing off, so you get less benefit for placing more magnet. So it's not meaningful to go further. Furthermore, as you saw, the reduction in volume is very serious, and the mass is greatly reduced even with this choice. Maybe we could make it slightly smaller, but is it worth it? That's another issue. Evet arkadaşlar. Peki bugünkü bu kadar. Öğleden sonraki sunuşlarımız var. Bir yemek arası verebiliriz. Teşekkürler.
Hocam ağzınıza sağlık.
Vallahi sağ olasın. Anlaşıldı mı bilmiyorum ama dinledin mi sen?
Fransızca sağlık.
Evet, şöyle.
Çok teşekkür ederim.
Evet, ben teşekkür ederim. Sağ olun.
Şöyle bir de buzumuzu da verelim.
Tamam,
hocam.
verelim.
Ne oldu İrfan? Kameraya çektin galiba.
O çekiyor bu yine herhalde.
Tamam. Hocam çok teşekkür
ederim.
ederiz.
Ben teşekkür ederim. Sağ olun Orhan Bey. Vallahi
İyi oldu değil mi?
efendim iyi oldu. Güzel.
Arkadaşlar teşekkür ediyoruz. Öğlenden saat biraz iyi oldu, vakit değil.
İyi oldu. 10 dakika erken bitirdik.
Tamam.
İyi oldu. Tabii. Evet.
Çektirdik.
Ya. Orhan Bey çok uzun durma ya.